to get started a little bit earlier, about a minute early, because I'm not as funny as Eric, I'm not as smart as Jeff, but one thing I do really well is talk for a very long time. So hopefully we can get this all in within the 50 minutes. So we're going to talk about how to fail with serverless today. This is not about a failure story where I tried to build something in serverless and it didn't work for me. This is about how, when you're building applications in the cloud using serverless technology, how we can deal with those failures gracefully so that we can make sure that our applications continue to work. So my name is Jeremy Daly. I'm one of the only people whose picture on Twitter actually looks like me in person. I'm the CTO at Alert Me News. It's a small company out of New York. I actually work out of Massachusetts. I have been doing some consulting with companies in the cloud for quite some time. I've been doing it for a very, very long time. If you say I don't look old enough, I really appreciate that, but I'm actually much older than you may think. I started working with AWS very, very early on, sort of when cloud computing started to really get popular, or started, I guess, early in the days, and then started working with Lambda in 2015, right after it sort of went GA. I also have a blog, jeremydaly.com. I do a lot of open source projects, and I do speaking. And if nobody has subscribed to the Off by None newsletter, please do that. It's a weekly roundup every week of a bunch of stories that are about serverless and things that are happening in the industry. And then I have my Serverless Chats podcast. It's a podcast I do every week. I talk to amazing people like James Beswick and some of these other people that are in the serverless space, and we just have a conversation about some aspect of serverless. I'm also an AWS Serverless Hero, which is a really great program that AWS has that allows me to get some insight into what they're working on and provide a good channel of feedback to them. All right, so the agenda for today, it's kind of packed. I'm sorry. I kept on adding slides because I'm like, well, they're going to need to know this, and they're going to need to know this. So we're going to talk about distributed systems in serverless. We're going to talk about writing code for the cloud. We're going to talk about the failure modes in the cloud. We're going to talk about a few serverless patterns that we can build to deal with failure. And we're going to talk about decoupling our services. This talk is going to reference a lot of things that are AWS. And a lot of these failure modes are specific to Amazon Web Services, but the patterns, the ideas, the thought process behind these are the things you should be thinking about regardless of which cloud you are building in. All right, so distributed systems, I know Jeff mentioned this a little bit. Distributed systems are separate systems that need to communicate with one another. And the way that they do that generally is by passing messages back and forth. All right, the other thing that's really important to remember about distributed systems is they're really freaking hard to build, all right, and even harder to kind of maintain. And the reason for that is, if you know this man, Werner Vogels, who's the CTO of Amazon.com, he has a saying that everything fails all the time. And that is incredibly true. And anybody who is sort of new to distributed systems, they have probably a lot of assumptions about the way that distributed systems work. Is anybody familiar with the 8 fallacies of distributed computing? Anyone? So there are 8 fallacies that your normal developer moving from sort of a traditional type of computing moving to the cloud or a distributed system would learn. So the first one is the network is reliable. We know that's not true, right? The network fails all the time. Routers go down. Packets are lost. Latency is not 0. We have a speed of light problem. We cannot get from England to the United States in 0 time because the speed of light can only move data so fast. We are competing with bandwidth, so the bandwidth, you're sharing bandwidth, that is not infinite. The network is not secure. Just somebody can put something on your network. You can't just trust every bit of packet or every packet of data on your network. The topology is always changing, right? You have things that are failing. You have things that are rerouting, things that are failing over. You have multiple people working in the system. It costs money to move data, and the network components are always different, right? So the thing about serverless applications are they're essentially distributed systems on steroids, right? And this is because we are breaking down the compute to even smaller distributed compute units, okay? They're stateless, which means we need to be able to communicate through the network in order to rehydrate state. They're uncoordinated. So if you think about microservices, maybe run on containers, you've got an entire stack of an application that can communicate within that stack. All of these individual components need to communicate with one another, so we need to use things like buses and queues and pub subs and state machines. We have to go even beyond what we would typically do in a normal distributed system. And they're also heavily reliant on cloud computing services, right? We love this idea of managed services. We call it serviceful computing because we don't want to have to reinvent the wheel. We don't want to install our own database server. We don't want to install our own Kafka or things like that. We want to use services that do it for us. All right, so what does it mean to be serverless? You've all been sitting here for quite some time listening to different definitions of serverless, and the things that you've probably heard are, well, you don't have to manage servers. Great. It's great at scaling, at flexible scaling capabilities. You pay for value, or some people say you never pay for idle, which is really not true anymore. But, and let's talk about things like automated high availability. Here's the other thing about serverless. It's a lot of configuration and a deep knowledge of the cloud services that you're using in order to make this stuff work. And the other thing is it's highly event-driven, so you have to be really conscious of how these events communicate with other systems. All right, so there are a lot of services in the cloud that we have to communicate with. You've got things that are sort of called serverless, and these are AWS services. So things like Lambda functions and SQS and AppSync and Comprehend, EventBridge, stuff like that. You've got managed services. Those are things like Elasticsearch or maybe Redshift or Elasticache, RDS, things like that. Then you've got a bunch of components in the cloud that aren't serverless, right? So anything that runs on a virtual machine is not serverless. And you have other things like Kubernetes and Docker and Kafka and MongoDB. If you're installing these on VMs, they're not serverless. So there are a lot of places in the cloud where things can go sideways, and they can go sideways very quickly. So for a very long time, when it came to computing, we were fixated on this term called reliability or high availability. And we still are, right? We still want to make sure that our systems are highly available. And what reliability really is about is this idea of maintaining some level of operational performance and having that uptime, right? So the 10 nines or 5 nines or whatever it is to try to keep our uptime. But really, with distributed systems, what we have to think about is what we call resiliency. And this is different than reliability, because this is the ability for us to absorb failure, right? When something happens to our system, we want to be able to absorb it and continue to provide some level of acceptable performance back to our users, right? So this is not about preventing failure. It's about understanding how to gracefully deal with it. OK, so let's move on to writing code for the cloud. Now, when we put code in serverless, right, we're gonna use something like a Lambda function. It's going to be a little bit different than just writing a big application, right? So Lambda functions are a little bit different than the way that we would write traditional code. That has to do with the fact that they're ephemeral, right? You're going to spin up a container. It can go away at any time, all right? It's event-driven. It runs in response to events, which means this thing isn't just sitting there able to do background processing. It's waiting for something to tell it to do something. It automatically manages the runtime, the compute, and the scaling. So you don't have a lot of control, which is a good thing for many reasons, but you also don't have a lot of control over how that's handling that for you. There is a single concurrency model in Lambda functions in most fast services. That means that for every concurrent request, it spins up a new container. That means that you can't share data between requests or between concurrent requests because of the way that the isolation modes happen. Also, there are no sticky sessions. There's no guaranteed lifespan of a container. A container can run for 10 seconds. It can run for 20 minutes. And you can't necessarily route somebody back to the same container. So you can't use those traditional methods of saving things, saving state, right? They're stateless applications. All right, so when we're writing a function normally, or we were writing any bit of code, the way that we would traditionally handle errors, right? How would we traditionally handle errors? Anybody know? Can make this interactive. You guys are all like staring at me. We could use try catches, right? That's something that we typically do, where we would try to do something, something interesting, something important, and if that fails, we catch that error, and we try to do some error handling there. Maybe we try to log some of it. Maybe we even try to retry that operation. But here's the problem with this in a Lambda function. What happens to that original event? Right? So an event comes in and it triggers this, and now your function fails and you try to do something. So maybe you want to log what that original event was. Maybe you want to retry the process or whatever it is. But what happens if there's a network issue and you can't connect to your logging service, or you can't connect to your database service to record that information? What happens if the function container itself crashes? All right? And then you don't even get a chance to try to reprocess it. And what happens if the function never even runs? What happens if an event goes and hits a function and that function for some reason never responds to it, okay? So this is sort of the captain obvious response here, but losing events is really, really bad, right? We don't want to lose events. All right, so Lambda functions have a couple different types of errors. Those are things like your normal, unhandled exception, something fails there. Lambda functions and other FAS, functions as a service, they have timeouts. They can only run for so long, right? So you could potentially get things like a function timeout. There are out-of-memory errors, right? You only have so much compute space available or compute memory available. And then there's this thing that are called throttling errors, where you can only run so many concurrent Lambda functions or Azure functions or whatever they are at once because there's going to be a limit to how far those can scale. Sometimes you want those to be there anyways. So there's all these crazy things that you potentially have to worry about when you're writing code for Lambda. So this is something that Eric Johnson kind of pointed out. The cloud is better than you at things like error handling, at retrying failures, at understanding network failures so it knows an event didn't make it to the processing or the compute that you need. It's really good at understanding its own network topology, right? So it can reroute things, and it can do things like handle failover and redundancy and those sort of things. So the question you have to ask yourself is, why not let the cloud do those things for you? All right? And this is what we're going to talk about today. And the way that you do that is by failing up the stack. And what I mean by this is that when we write Lambda functions or we write functions as a service, we don't want to catch the errors there. We want to fail the entire function and let the calling system handle that. Now this, I'm going to put the caveat on this that it's sometimes, right? For sometimes we do want to catch things, but for the most part, depending on how we're building our applications, we just want to fail the function, all right? This allows us to return the errors back to the invoking service, and then we can configure things like the retry mechanisms that are built into the cloud to reprocess events, and then we can utilize dead letter queues, which we'll talk about. I think some people have talked about those before, to capture those failed events. All right, so the thing that we have to think about when writing these Lambda functions, and you're going to say to yourself, well, I got all kinds of code. I need to be able to catch errors in here because I've got multiple services calling one another and all kinds of things like that. What we have to think about here is sort of the structure of how we code our Lambda functions. So I tend to believe there are 3 different types of Lambda functions. The first one is the Lambdalith, and we're going to talk about each one of these individually. This one scares me a little bit. There's something called the Fat Lambda, which is can be useful, and again, we'll get into detail. And finally, there's the single-purpose function, which is the way you want to go. So let's talk about the Mighty Lambdalith, if you remember 2001 Space Odyssey. This is the updated version of this, the Amazon Cloud version of the monolith. But essentially, your entire application is jammed into one Lambda function. And look, for all intents and purposes, a Lambda function or an Azure function or a GCP function, those are just mini Linux servers that can run information for you or that can process something for you. All right? Oftentimes, you see these are being used to lift and shift things like Flask apps or Express.js apps. The events are most likely synchronous against these, right? So they're usually synchronous API calls, either with something like API Gateway or ALB. And here's the big problem. Partial failures, right? So I try to make a call to my database. I try to do this, try to do that. Those have to be handled in the code, okay? Because you usually have multiple things happening where those need to be handled in the code. All right, the next one I call the Fat Lambda. I think other people call it the Fat Lambda as well. This is when you take several related methods and you co-locate them into a single Lambda function. Now, this is often used to optimize synchronous operations. This is when you may have to do multiple things as part of a single API call. And if you were trying to either do some sort of function chaining or something like that, this just wouldn't work really well. So partial failures are still handled in the code, something you have to think about. But I will caveat this with, under the right circumstances, this can actually be a really useful capability, right? Especially if you have a synchronous pattern that has to do multiple things, this can be very handy. All right, so finally, the last version is the last type is the single-purpose function. So this is a tightly scoped function, all right, that will handle a discrete piece of business logic. And what's great about this is that this essentially means that you're doing one thing and you're doing one thing well. All right, you can invoke these synchronously, you can invoke them asynchronously. We'll talk about a couple different ways in which you might do that. And failures are generally total failures, right? So if I have a single purpose function that all it does is write some data to DynamoDB, if that fails, I can fail my whole function. I don't have to worry about anything else failing or any other partial failures within my code. These are great because they can be reused as part of other workflows. We'll talk about state machines in a little bit. And they can be scaled or throttled individually, which is a really, really cool feature because that means if we're doing PDF processing, we can have hundreds of PDFs being processed, and it has no effect on our sign up our user flow or something like that. And what's great about these too is that you can get really tightly scoped IAM permissions. So you can use that principle of least privilege, and you can say, this function only has to put items to DynamoDB. Great, that's all it can do. All right, so let's talk about failure modes in the cloud. Now, this is where it's going to get a little bit complicated, so I'm going to warn you. There are just so many potential things that can go wrong in the cloud, and there are so many ways to handle these things. So I'm going to go through these relatively quickly. I don't expect anyone to be as geeky as I am and to read through all the documentation and figure out what all these things are. But hopefully, if anything, look at my slides later. You can use it as a reference because I compiled a bunch of information for you. So let's talk about retries. A couple things. They're vital to a distributed system. Okay. Most clouds and most cloud services will guarantee that at least once delivery, which means your event will get there at least once. But it is possible that the same event will get there more than once. And in order to do that, whenever we're using a system that's going to retry an event or retry an operation, we need to make sure that that's idempotent. Jeff talked about that briefly, so let's talk about it again, because I have the slide. Essentially, what idempotent means is that you can repeat something multiple times, and it's going to have the same result. And really, the key here is no side effects. Think of it as a pure function if anybody is into functional programming. So some idempotent operations would be things like updating a database record. If you send the same data to the database over and over again, maybe the modified date changes, but for the most part, the record stays intact. You can authenticate a user over and over and over again, and that's not going to cause any problems. And if you're checking to see if a record exists and it doesn't, and then you create one, you could retry that operation multiple times, and if it already exists, it wouldn't create a new one. There are a lot of strategies around idempotency, and these are certainly something as you start to work with the cloud and you start to work with anything that's going to do distributed systems, you really want to look at these and understand some of these. Jeff mentioned this idea of using an idempotent ID. Certain APIs like Stripe, for example, allow you to pass in an idempotent ID that will make sure that it doesn't charge your credit card twice, for example. All right, so just quickly about dead letter queues, just because I couldn't find the right place in my deck to put this because everything is so intertwined. These are just a way for you to capture messages that fail to process or are skipped, right? Sometimes messages don't fail. Sometimes they just get skipped for a number of different reasons. These are great because we can set alarms on them. We can inspect the events that are in there, and we can replay them sometimes if we want to be able to replay them. In AWS, these can be added to our SQS queues. They can be added to SNS subscriptions. They can be added to Lambda functions, so there's quite a bit of power there. All right, so in order for us to understand failure modes themselves, we have to understand how the different types of invocations of Lambda functions trigger these different types of retries and different types of failure modes. All right, so the first type is synchronous. This is very common. I think everybody understands how synchronous models work. It's a request-response model. I send a request. I wait for a response. Asynchronous, this is the set it and forget it sort of thing. My Boston accent just came out there. It's essentially where we just say, hey, make my coffee, and I wait for that, as Jeff said. The other type is something called stream-based. This is where you have certain systems like Kinesis and DynamoDB streams that actually push data to our Lambda function. And then we have something called polar-based, where our Lambda function has a service that will pull SQS queues. All right, so synchronous Lambda retry behavior. This is super exciting stuff. All right, so functions are invoked directly using some sort of request-response method. The failures for these are returned to the invoker. Okay, so if I try to invoke a Lambda function synchronously, it's just going to send that, and it errors out. It's going to send the message back to whatever invoked it. The retries, in this case, are actually delegated to the application that tried to invoke it. If your Lambda function is being invoked synchronously, which it is by a number of AWS services, some of them will automatically retry those for you. So think about idempotency. Like Alexa and Cognito, for example. If you have an Alexa skill and it tries to contact your Lambda function and it fails because it can't reach it or there's a throttle or something like that, it'll actually retry it a few times before it will go ahead and kick the error back. Other services don't retry, so things like API Gateway, ALB, which is the Elastic or the application load balancers, and step functions don't retry automatically. That has to be handled by the service itself. And finally, API gateways and ALB can actually return errors directly to the client because they are sort of an HTTP client interface. All right, asynchronous Lambda retry behavior. So the Lambda service, this is not a Lambda function, this is the service itself, can accept requests and it adds them to a queue. So when I send that message to my Lambda function and say, I want you to process this when you get a chance, that actually is queued for you. What happens is that invoking service will connect. It'll say, here's my function, the Lambda service, or so here's my data or event. The Lambda function says, great, I got it. Or the Lambda service says, I got it, and it sends a 202 status code back, and then it disconnects. And then that's where Eric talked about, you can just go ahead and respond back to your client that says, we captured your request. So this is where it gets kind of interesting. The Lambda service, by default, will try to reprocess your event twice. Okay, you can change that now with maximum retry attempts, where you can set that to either 1 or 0. But essentially, if it tries and your Lambda function fails, it'll automatically try again because, again, we've disconnected, so we have no way of knowing whether it succeeded or not. If, for some reason, that Lambda function is throttled, then it'll actually retry for 6 hours. And again, this is another thing that you can change now with those capabilities. And you can take failed asynchronous events and you can send them either to a DLQ, which we talked about, which would be something like SQS or SNS, or there's this new thing called Lambda Destinations that we can use for an on-failure event. All right, so stream-based Lambdas. Okay, this is, again, if I'm losing you here, just start waving at me and I'll go faster. But essentially, these records are pushed synchronous. And I'll be honest, this stuff fascinates me. It's super cool stuff if you're kind of geek out on it. But I understand it does. You're probably like glassing over. But anyways, I'll send you my slides. Anyways, records are pushed synchronously to Lambda, all right, from Kinesis or DynamoDB streams. That means that the DynamoDB stream or the Lambda or the Kinesis stream is going to wait for the Lambda function to respond with either a success or an error. Okay, and this comes in batches, so they come in these huge batches, or up to 10,000 for Kinesis, and 1,000 potential record batches or records in a batch for DynamoDB streams. So there's something called the maximum retry attempts. By default, this is 10,000, which means that if you have a bad message in your Kinesis stream or in your DynamoDB stream, if your Lambda function keeps failing, it's going to keep failing 10,000 times, right? So this is just something to be careful of, where you need to understand, you might not want to retry it that many times. There's also something called the maximum record age in seconds. So you can say, look, if I don't process this after 5 minutes, then just throw that event away. I don't have to worry about it. I only want the events that happened after that. So that's a good way to cut it down. There is a new thing that is very, very cool called bisect batch on function error. And what this does is, let's say that I have 100 items in my batch. It'll send those 100 items to the Lambda function. The Lambda function will say, nope, I'm failing. Something in this is failing. So then what it'll do is it'll split it, and it'll say, well, here are the first 50. And then here are the second 50. If the first 50 fails and the second 50 works, then what it does is it can retry that 50 again by splitting it to 25 and 25. And then it splits it to, that'd be interesting, I don't know, 12 and 13, whatever it would split it to, but it'll keep splitting it until it finds that poison pill. And then there's also on-failure destinations for stream processing. So if a record is skipped, right, because it doesn't work or whatever, then you can go ahead and send that to SQS or SNS. All right, so polar-based lambdas, this is only really applicable if you're polling an SQS queue. It is a synchronous operation as well, which means that the polar service, this is different than the Lambda service and different than the Lambda function itself. This Lambda polar will wait for the Lambda function to say whether or not it was able to process it or not. If it was, it removes it from the SQS queue. If not, it will put it back. Their batches are very small. There's only 10 per batch. but it will fail the entire batch, right? So if there's one problem, it puts them all back in, and it would keep retrying those same 10 over and over again. It's not a perfect system. There is a max receive count that you can set, though. So if you get the same message 5 times, it gets returned to the queue, then it can go ahead and DLQ those. There's a polling frequency that basically is automatically determined based off of the concurrency you set. So if you want a very low concurrency, say you only want to process 10 concurrent requests with your Lambda function, then the poller will adjust itself to handle that level. But there are some things like visibility timeout where you have to make sure you set those to 6 times the timeout configured on your consuming function. Literally only put this in here so that you'd have it when you look at the slides later. I don't expect you to remember it. All right, so Lambda Destinations, this is a really cool thing. This only works on asynchronous invocations, which we talked about. You can route these messages not only on failure, but also on success. And I'm going to show you a pattern in a little while that, that allows you to use this on success thing to process events on the back end. If you noticed, or if you've been paying attention, dead letter queues and on failure Lambda destinations are almost the exact same thing, right? So you can use either one. You should use on failure now. That's sort of the best practice or leading practice, whatever you want to call it. The reason is on failure gives you a whole bunch of context, right? So you'll get the stack trace. You'll know more information about why it actually failed. And then you can do some cool things with that, which again, I'll show you in a bit. All right, so the other thing is that destinations can be to an SQS queue, they can be to an SNS topic, they can be to a Lambda function, and they can also be to EventBridge, which is the event bus that AWS has that James talked about earlier this morning. Couple sort of nuances, I guess you could say. The JSON format that gets sent from Lambda destinations or on Lambda destinations is specific to who you're sending it to or what service you're sending it to. So if it's SQS or SNS, it sends it as the message. If you're using a Lambda function, it passes as the payload. And EventBridge does a couple of funky things. The detail is the output, but then the source is set as Lambda, which is not AWS Lambda, which every other event that comes from AWS Lambda is the source of AWS Lambda, but that's okay. And then the detail type is either Lambda function, invocation result, success, or failure, and then you get some information about the ARNs of the function and where it was sent to. Okay, so are you guys all still with me? Right, nobody's passed out and smacked their head on the desk yet. So SQS has what we call redrive policies. This is another failure mechanism that we can do, which means that if you return a message to an SQS queue multiple times, that once it exceeds that limitation, you can put it into another SQS queue so that it isn't blocking your application anymore. That's the dead letter queue we talked about. We can go back and inspect those and replay them if you need to. So they're only sent if that maximum value is received. Yeah, sorry, skip over to the next thing. So then SNS also has redrive policies now with its new support for dead letter queues. So they are supplied, or the dead letter queue is assigned to the subscription, not to the topic, right? So you may have a SNS topic. If you're familiar with SNS, it's a pub subservice. You can have it go to SQS, you can have it go to HTTP, you can have it send emails and SMS messages. So what you don't want to do is if your SMS message fails or your triggering of an SQS fails or something like that, you don't necessarily want to write all that data back to the same queue. So you can actually do that based on the individual subscriptions, which is kind of cool. It only supports SQS, right? You can't just send it back to another pub sub and have it keep distributing out. So client-side errors, if for some reason it can't connect to something like the Lambda function doesn't exist, it won't retry. But any messages to SQS or Lambda will actually be retried 100,000, 15 times over 23 days. So I typically make the joke that SQS or SNS to SQS is pretty much guaranteed. And when the coronavirus comes and wipes all of us out, the good news is that your messages will still be delivered from SNS to SQS. So we don't have to worry about that. Anyways, messages to things like SMTP or SMS or mobile, they get retried 50 times over 6 hours. And then HTTP endpoints, which is kind of a cool feature of SNS. You can do some weird proxying stuff that comes up with some interesting patterns. But you can actually control those, right? How many times it retries, what you want the delay to be, what you want the backoff strategy to be, if you want it to be linear or something like that. All right, then EventBridge, we talked about that quickly. So that is a similar, sort of simple retry where it just keeps retrying for 24 hours. There's a backoff built into that. Lambda functions are invoked asynchronously, which is super helpful because then we can use Lambda Destinations when a message gets sent that way. Failed events, which again are very, very unlikely because again it tries for 24 hours, but if they were to fail, they would actually be lost. And this is an important point. That retry in EventBridge is really only meant to get the data to the service that is the destination service. So for example, it'll retry for 24 hours for the Lambda service to accept the message. Once the Lambda service accepts the message, then all the failure modes of those downstream services are used. If you deliver it to SQS, once SQS accepts the message, then all the redrive policies happen there at that next level. All right, the other thing we got to talk about quickly is step functions, because if you are doing complex workflows in the cloud, step functions are really, really helpful. They are orchestration workflows or state machines, if you're familiar with state machines. This is an example actually that Yen Trey, who is also known as the Burning Monk, put together. This is the Saga pattern using step functions. You could do something similar with logic apps and things like that. But essentially what this does is it allows us to create these complex error handling patterns, right? So the Lambda functions in this case are also invoked synchronously, which means when the Lambda function fails, it immediately, or that the state machine will wait for that Lambda function to respond back, whether it fails or didn't fail. This is really cool that it does that because we have these things called retriers, and I don't think retriers is a word, but it's on the website. And also catchers that will determine based off of things called error names. It can condition the error handling. So you might get states.all, which is sort of the fallback, but you can get states.timeout, you can do states.exception. There's a couple of other things that you can use that you can actually customize or have different failure paths based on the error that comes back. And you can also control the retry policies themselves on every one of these tasks using things like interval seconds, max attempts, and the backoff rate. So step functions, very, very cool stuff. All right, got another slide here where I had no idea where to put it in the presentation, so I'm going to just show it to you now. If you are writing code in the cloud and you are writing Lambda functions, you most likely are going to use the AWS SDK of your choice for Java or for Node or for Python, and you're going to use that to communicate with AWS services. All right, so this actually has built in, and I've seen people, and I've done it myself because I sometimes didn't trust this automatic retry, try to build in their own retries calling AWS services with the AWS SDK. You do not need to do that. The retry stuff works pretty well. There is this complex chart, which again, I only put it in here so that you can look at it afterwards on the slides. But depending on which SDK you're using, there are different timeouts, connections. I mean, again, the maximum retry count on Node, it depends on the service. So again, look those up if you want to see more information about those. All right, let's get into some of the fun stuff. So this is the error handling patterns. And essentially what we want to be able to do is come up with a couple of patterns that are sort of common to use cases on the cloud, and that we could apply those immediately and be able to handle some errors or handle some issues or potential failures. So the first one is a simple caching strategy. All right, so let's say that you have a client, it calls API gateway, and you're communicating with a Lambda function, and you want to query something that isn't serverless. And by the way, this is something that is very, very common in serverless applications. Is there are a bunch of things that aren't serverless in them, right? You're communicating with RDS, you're communicating with some API that can't scale, or it's going to have quotas or throttles or something like that. So in this case, we want to get data out of an RDS. So let's say we have a read-heavy application. Well, the problem is that what happens if that RDS cluster goes down? What happens if we exceed our connection availability, things like that? What's really helpful is to put something like Elasticache in. Now again, if you're already using RDS, adding another thing that's not serverless really isn't that big of a deal. So we put Elasticache in there, you're already in a VPC. If we get a hit on this, then we can respond immediately back to our client and say, hey, here's the data you were looking for. If we try to do this though and we get a miss, right, then that's when we actually communicate with the database, pull some data back, and we have to write that back to the cache because we are not using a write-through cache, so we do have to manage that caching ourselves. Then we can respond back to the client. So a couple of key points here is that we want to make sure that we only create these connections to the database when there's a miss. We want to make sure that we have our time to live set properly so we're not caching data too long. And we want to make sure we include the ability to invalidate the caches. Now, the reason why this is good pattern for failures is because if that database goes down, it's possible for us to use a circuit breaker, and I'm going to explain that in a minute. But we could basically respond back to the client when we had the data, and if we didn't have the data they were looking for because our database was down, then we could go ahead and respond back to them anyways with some information. And again, if there was a whole bunch of traffic for some reason and it was overwhelming our database, then we have a little bit of a buffer here. And I know what you're thinking. Everybody who's taken a computer science class on databases knows that you shouldn't put a cache in front of a database to prop up the database if it can't handle the load. Totally agree with that. So you still need to size your database clusters appropriately depending on what you expect the traffic to be. But this is a good way just to add some mitigation in case that goes down, or if for some reason the traffic spikes really high at some point. All right, the other thing is this idea of buffering our events for throttling and durability. So this would be like a write scenario, maybe a heavy write scenario. We're doing a webhook. We're doing something like that. So we have our client. It contacts API gateway. Maybe this is the Stripe API that's sending events to us, or they're the events coming from SendGrid. And we want to get that data into RDS. All right, so this is where we could add an SQS queue, and this is sort of what Eric Johnson was talking about, the storage first type thing, where we take the data, we're using Lambda as a transport here, which we don't need to use. I'll show you that in a second, but we're pushing data into the SQS queue, and then this disconnects, and we can say, great, we got the data, and we can respond back to our client and say, hey, we got your data, where we'll process it. Then what we do is we put another Lambda function in here, which we set that function concurrency to so that we can throttle it, right? So this way, we want to make sure we limit that concurrency so it's not going to overwhelm our RDS. Now, this happens all the time. You get some massive spike. Let's say you send out an email to an email list of 100,000 people. Well, guess what? In the next 2 to 3 hours, you're going to get thousands and thousands and thousands of events from SendGrid, and you need to scale up for that. The problem is your RDS cluster, you're not going to have it scaled up necessarily for that. This gives you a way to limit it, or to protect against that, because you can buffer those events, and you're not going to lose anything. So what happens here is that Lambda function will actually query or pull the SQS queue. The data will get written into RDS, come back, and then we can reply back to the SQS queue and say, hey, we got all the data. And that happens automatically as part of the polar system. But if for some reason it was to fail and we couldn't write the data, then after our redrive policy kicks in or whatever, we can write that data to a DLQ. So maybe there is an event that comes in that our system doesn't understand, our function keeps failing it, we can just write that to the DLQ, and we don't have to worry about losing those events. So a key point here, and this is one way that we can really add resiliency to our system, is by adding that durability with a queue in front of it, right? SQS is super lightweight, it's highly scalable, you can throw millions of events at it, and likely you're going to have very few failures. So if you do have a big spike like that, it's going to perform a lot better than RDS, and then you can use that Lambda function and that throttle nature to eventually chew through that data. So that's one of the big things about throttle lambdas. They can reduce that pressure on those downstream systems. And then, again, if an event fails, we can store that in that DLQ, and we can look at it later. So this is one of those things where Eric talked about service integrations. So you could actually get rid of the Lambda function here and just dump that data right into SQS. And I would actually, one of the things I do with the Twilio webhook that we've got set up is I just dump the data right into SQS, and then I use the function that pulls it to verify data and make sure that it's the right shape and so forth. And you can do some of that in VTL templates if you're familiar with those, but it gets a little bit more complex. All right, so the circuit breaker pattern, this is one of my favorite things. Jeff actually alluded that he was going to cover it, and I was like, oh no, and then he didn't, so I'm going to tell you about it. And essentially what it is if I am wanting to communicate with something like the Stripe API from a Lambda function, the happy path is I send a request to Stripe. Stripe says, oh, I processed the credit card, here's the information back, and you can go ahead and respond back to the client. Now, this could happen asynchronously as well. It doesn't matter whether you're using API gateway to trigger the Lambda function. The point is something can go wrong. And like I said in the beginning, everything fails all the time, right? So if this happens, then what we need to do is figure out a way to say, if we can't reach that Stripe API, the worst thing we can do is continue to DDoS some application by sending events over and over and over again when it's like, hey, I already can't handle it, so it'll swamp that event even more. It'll make it harder for it to be harder for it to recover. So for us to be good, what do they call them, netizens or whatever it is, good citizens of the internet, we want to make sure that we don't overwhelm other services, right, because we're going to increase the problem and it's not going to help. So what we would do here is we would put some sort of a status check in between the Lambda call to the API, and we would use some cache, whether that's DynamoDB or something like Elasticache. We would go ahead and check and say, hey, is this service available to the best of our knowledge? And if it is, then we go ahead and we call the Stripe API. This is what we say when we say the circuit is closed, right? If you think about how electricity works, if the contacts are touching, it's closed, then the circuit, it completes it, and the light lights up. If you open it up, then it disconnects. So if it's a successful attempt or call to the Stripe API, we simply return to Lambda functions, reply back to our client, everything's good to go. But let's say that it fails. Let's say that we try to call that Stripe API and something happens, it doesn't work anymore. Then what we do is we actually want to go ahead and start incrementing a failure count in our cache to let our system know, hey, we might have a problem coming up. And then we can respond back to the client. And again, if this was something where it was pulling from an SQS queue, there's all kinds of retries built in. I mean, you can imagine the different patterns you could do there. Then we can reply back immediately and say, hey, there's a problem. So now what happens is the next time a request comes in, we check our cache, and our cache says, no, this database or this API is not working. So then we can immediately respond back to the customer and say, nope, we're throttling, or we're not sending these now, or whatever, or if it's an SQS queue or something like that, we can buffer those events. What we do need to do, though, is we can't just say, hey, it didn't work, so we can't ever contact it again. So what we do what's called half open, right, where we basically say, hey, let's send a request to the Stripe API maybe once every minute, maybe once every 30 seconds, maybe more than that depending on your use case, and say, hey, are you working now? So if it doesn't, if it still fails, then we say, okay, great. We just respond back to client, no problem. But if it succeeds, now we can update our cache, and we can go ahead and open that again, or close that circuit again, and now all the new events that come in, we're going to go ahead and route those back. So a couple of things here is that if you're using this pattern, you'd want to cache your cache with warm functions. The way we didn't really get into cold starts and all that kind of stuff is way too much to cover, but the same Lambda function can be reused over and over again. You can use the global scope to save some information. It's a good idea not to be contacting Elasticache or DynamoDB on every single invocation. That might create too much traffic and get really expensive, so we check that periodically. We can cache some of that data. You want to use a reasonable failure count. If you have 1,000 events coming in or 1,000 API calls being made every minute, you don't want to fail after 2 failed attempts, right? You may want to fail after, I don't know, 2,000, 3,000. You want to have a high enough failure count where you know the system isn't working. And then finally, you really have to understand idempotency here, okay? And I talked about Stripe having the idempotent ID that you can send in, which is a very helpful way for you to minimize sending or to not process the same event multiple times with some impact on the system. All right, so here's a new pattern that I came up with. This is sort of recently available now that we have things like on failure and on success from Lambda functions. So this pattern works really, really well if you are doing some sort of background event processing, right? So maybe somebody placed an order on your website, and you have a task that's set up or an event processing a Lambda that takes that information of the order and checks Marketo or checks Salesforce or something like that and maybe inserts a record in there. So it really doesn't have to do anything that's coupled to these other events. It just needs to do some bit of processing. Right, so if we use EventBridge in this situation, we would create a rule that says, hey, anytime a new order is created, route it to this processing Lambda. We've got some events that come in through EventBridge, and if that picks up one of those events, it sends it into the processing Lambda. Now, if it succeeds, right, great. We can send the message, we could do nothing with it, or we could send a message back to EventBridge that says, hey, we've just added this customer or updated this customer's record in Salesforce or something like that. And then if any other downstream system is interested in picking that up, then that's great. It's on the event bus. They can do something with it. And those will just send out those additional things. If it fails, though, we can use the on-failure destination, and we can send that message to EventBridge as well. But we want to take those messages and put them into a dead letter queue if they're failed events that we know we can never reprocess or meet some criteria that they're not going to be reprocessed. And we need to inspect those. So we can add a rule to EventBridge that basically says, listen, we want to route any permanent failures to this SQS. If one of those is picked up, it routes it there. But the other thing is that we may have events that come in that fail for different reasons, right? Maybe the API for Salesforce was down, right? So that's not a failure that is a permanent failure. That's a failure that's more transient that we want to be able to retry at some point. So we want to be able to replay that. So we can create another rule where we create retryable failures. I know that's not a word. That's why I put it in quotes. But essentially, that can pick up any events that have a pattern that says, yeah, these are retryable. So we send them into the replay SQS queue, and we can use something like the delivery delay feature of SQS, which allows us to say, hold this in the queue for a minute before anybody can pull it back, or 5 minutes or something like that, so we can use that as a way to sort of throttle and not overwhelm something that might be down. And then we can also put a replay Lambda here that would be throttled, right? Because we want to make sure that if for some reason we get some massive amount of failures coming through, we don't want to just go ahead and retry all of them right away. We can pull that queue, and then we can actually send an asynchronous request either directly back to the processing Lambda, or we could put the message back into EventBridge. I have a version of this that I posted on Twitter that I had it going into EventBridge, and some people commented, well, what if you have multiple rules that would pick up the same thing? That's a good point, and you might not want to retry some of those. So you could definitely do something this way. So anyways, interesting pattern. Lots of cool things you can do with on-success and on-failure destinations. EventBridge has all kinds of great rules that you can use. You can change things around and decide what gets sent to different things. All right, so quickly I want to talk about decoupling our services, because this is an important aspect of sort of thinking asynchronously, but also being able to handle and mitigate failure, because we can isolate failure into separate services. Right, so SNS, this is our pub sub service. We can actually do multicasting with SNS, and that means that we send a request to SNS, we get our ACK back, we know that we have it. SNS can actually act like an event service in and of itself, and we can send messages to multiple targets. So we can send them to SQS, we can send an email to somebody, we can hit an HTTP endpoint, we can trigger another Lambda function, and if any of those fail, we can create dead letter queues that map against those. So some key points on this. SNS is a very well-defined API, so you can call it from multiple services if you wanted to use it as an event bus. This decouples those downstream processes, and it allows you to create all those different consumers, and you can filter in terms of which one gets which event. All right, I would highly suggest, though, that you move to something like EventBridge, because EventBridge is a little bit sort of built for this particular purpose. Same idea. You send a message to EventBridge. This is an asynchronous request in the sense that the client says, hey, EventBridge got it. I'm going to disconnect. You get an ACK back, and you actually get an event ID, which you could use to track if you wanted to. So this can send to things like SQS and Lambda, but it can also send to things like step functions or another event bus in another account, and plus 16 other services that it can deal with. And every single one of these can have rules to determine whether or not it gets a particular message. So multiple subscribers, rules, patterns, and filters. I'm running out of time. You can forward events to other accounts, which is really interesting. And then, like I said, it's got that 24 hours of automated retry. So when would you use these sort of patterns, and how does that kind of fit into failure and some of these other things? I know you're asking yourself that question. So let's say we call API gateway, we hit a Lambda function, it does some processing or whatever. We send a message to EventBridge. Now, that gets an ACK back, and we can send some message back to the client saying, okay, we got your event. Now we could do some really interesting things with it. Let's say we have an order service, okay? This has its own SQS queue. It's connected to an RDS. It's got a Lambda function in between there that's throttled, right, so that we can manage the throughput and so forth. The SQS queue can have a redrive policy, so if messages get sent back to it, they can be reprocessed. We can send things back to EventBridge. The point is that order service is its own discrete service, right? And the failures that we build into that are their own. And so we can subscribe this service to the EventBridge. And so when a message comes in that picks up that says, oh, an order was placed, great, I'm going to go ahead and use this order service and trigger that. But what's great about this is then we can add an SMS alerting service, right, and create a rule that says, hey, if an order was placed, then we want to go ahead and make sure that we send a message to the Twilio API. We don't want to overwhelm the Twilio API, so we're going to add in some throttling. Maybe we'll add in a pattern that we can do some quota management. And then maybe we have a billing service where we actually charge the credit card, right? So we have another rule, that contacts that, hits our SQS, does it, contacts the Stripe API. Maybe we implement the circuit breaker within that service. We can implement all those great failure modes, and they're completely isolated from our original client passing that message. right? So these rules are actually really cool and complex, so you can create something that's as simple as matching, hey, the order was completed, so we're going to go ahead and send a message to the SMS alerting service. It could be something where you look at these patterns, and maybe you say, well, if it was a free service, if it was a free order, maybe somebody was ordering like an ebook or something, and that was for free through our site, then we don't want to charge them. So we'll just let them do that. And so you can do a lot of complex patterns around that. So filter events and selectively trigger services. You can manage the throttling, the quotas, and the failures per service. And then you can use Lambda Destinations with asynchronous events. So key takeaways here. Be prepared for failure. Everything fails all the time. It's fine. Okay? All you got to do is utilize those built-in retry mechanisms of the cloud. Don't try to do these yourself. Understand the failure modes, right, that you can use to make sure you protect against data loss. Buffer and throttle events to distributed systems. The more distributed your application is, it sounds scary, but actually it's easier to isolate failures when you do it that way. And other thing is, embrace those asynchronous processes to decouple components. Just gives you more control and some more flexibility with your systems. All right, so these are a couple things I'm working on. Check out the Serverless Chats podcast. Sign up for my newsletter. DynamoDB Toolbox, some good stuff. Lambda API. My GitHub, my Twitter, and so forth. Thank you very much. Take the Serverless Community Survey. I put the thing right there. Boom. Right on time. Just went to 0. So anyways, thank you very much. I appreciate it.